The idea of a nanochemical mechanical computer feels almost contradictory. On one hand, the term computer evokes visions of silicon chips crunching numbers at gigahertz speeds, training vast AI models, or simulating galaxies. On the other, swarms of nanomotors drifting in fluid seem anything but computational. Slow, noisy, erratic. To many, these pictures do not align. How could twitching beads in a droplet ever deserve the name of computation? And yet, a haunting question lies at the center of this vision. If motion itself can embody information, then could a fluid full of motors become a processor? Not of numbers at lightning speed, but of bits at the ultimate efficiency allowed by physics. From the scientific perspective, the bridge is thermodynamic efficiency. Silicon logic gates burn orders of magnitude more energy per bit than Landauer's limit requires, wasting heat in every transition. Nanomotor systems, by contrast, already live on the boundary where thermal noise and chemical work are nearly inseparable. Each tumble, each biased step against a gradient comes at an energy cost not far above the fundamental minimum. The promise is not exaflops per second, but bits per joule, approaching the physical floor. Doesn't this suggest that the real comparison is not about speed, but about proximity to nature's ultimate accounting? Engineers add the complementary layer, context. Electronic processors cannot operate submerged in blood, river water, or corrosive solvents. Nanomotor ensembles not only survive, but exploit these environments, computing directly where the information resides. A chip of motors might map toxins in a waterway or diagnose disease from within a drop of blood, processing signals chemically, with no wires or batteries. These systems would not compete with AI supercomputers, but they would pre-capetch information before it ever leaves the medium, acting as self-pointered filters and encoders. Could it be that the most valuable computers of the future will be those that never leave the sample they analyze? A lesser-known perspective is conceptual. Once one accepts that computation is not confined to silicon, the definition expands. In silicon, voltage pulses represent bits. In quantum computers, superpositions of qubits do. In nanomotor systems, trajectories themselves are the code. Biased walks encode gradients. Feedback loops rectify randomness into signal, and mutual information quantifies what has been extracted. The laboratory becomes an unusual computing pipeline. Gradients inscribe data into space, motors read it by moving, and cameras decode it into digital form. Reframed this way, what looks like slow diffusion is, in fact, ultra-efficient in situ computation. The paradox, then, is that such computers would be both weak and powerful. Weak in speed, scale, and generality, but powerful in efficiency, context, and survival where no transistor can function. Out of noisy motion emerges clarity, out of chemical dissipation emerges bits, out of apparent slowness emerges immediacy, since the computation happens right at the source. The haunting question is not whether such systems can rival silicon or quantum machines, they cannot, but whether they will carve out an entirely new dimension of computing, one where the smallest possible engines deliver the smallest possible cost for a bit of certainty. Conventional computing relies on electrons in silicon, or on qubits in fragile quantum states, both optimized for speed and large-scale logic. A nanochemical mechanical computer, by contrast, uses nanomotors, or molecular machines, whose trajectories encode information directly in chemical or fluidic environments. Instead of maximizing flops, such a system maximizes information per joule, approaching the fundamental Landauer bound. Here, computation is not the execution of algorithms on bits in memory, but the extraction of patterns from the noisy dynamics of particles. Every fluctuation that a nanomotor rectifies or every gradient it follows doubles as a computational act. This reframes computing as an embedded, energy-bounded process tied to its environment. A swarm of catalytic Janus motors in blood could encode the presence of glucose gradients by biased motion rather than by transistor switching. It is like writing with footsteps in sand. The path itself is both the record and the computation. Electronic computers will always win in raw speed and logic density, since electrons switch orders of magnitude faster than molecules diffuse or motors swim. But the nanochemical mechanical paradigm is not about outrunning silicon. It is about operating where silicon fails, inside fluids, cells, and chemical reactors. Its value lies in reaching the thermodynamic minimum of energy per bit, performing sensing and decision-making without external batteries. This shifts the axis of performance from exaflops to joules per bit and context adaptation. By embracing slowness, such computers unlock ultra-efficient, autonomous operation embedded in real environments. Efficiency, not speed, becomes the metric of superiority. A diagnostic chip computes the presence of toxins by observing motor paths powered by the toxins themselves, consuming no extra energy. It is like a sundial, not fast, but unbeatable in energy efficiency because sunlight itself powers the measurement. In this paradigm, nanomotors act as both transducers and processors. Their motion through gradients or fields encodes environmental data. The bias of trajectories, their step-length distributions, and their turning statistics form a natural alphabet for computation. Algorithms are not software running on hardware, but statistical inference performed by decoding trajectories. Mutual information between paths and signals quantifies the computation, while chemical-free energy spent fuels the encoding. Every joule spent on propulsion is simultaneously spent on acquiring bits about the environment. Thus, motion is message. By tracking motor headings in an electric field, one can reconstruct both field direction and strength with measurable information yield. It is like hearing meaning in the rhythm of drum beats rather than reading printed letters. Stochastic thermodynamics supplies the framework for energy to information conversion at this scale. Work done by motors, heat dissipated into the bath, and entropy produced along paths are all linked to information measures. The Landauer bound and fluctuation theorems define how many bits can be extracted per joule. A nanochemical mechanical computer thus turns the noisy bath into a resource. Entropy produced is the unavoidable toll paid for precision. The paradox is that wasting energy is also the price of learning. Computation is embedded in the same flows that keep motors moving. A peroxide-powered nanomotor consumes molecules, dissipates heat, and in doing so reveals the gradient direction as recoverable bits. It is like burning a candle both for light and warmth. The same energy serves two inseparable purposes. Adding feedback control transforms nanomotor ensembles into information engines, systems that rectify noise into directed work based on real-time measurement. Controllers can nudge motors only when fluctuations are favorable, amplifying weak signals into reliable outputs. Performance metrics include bits per joule, energy per bit, and detection fidelity per dissipated watt. Here, the computer is not a static circuit but a dynamical loop, measuring, acting, and learning in one continuous cycle. Such feedback devices extend Maxwell's daemon into fluidic microsystems. The paradox becomes operational. Noise is not an enemy, but a computational fuel. A GPU-based loop pulses an electric field when a motor is heading correctly, boosting chemotactic accuracy with minimal added energy. It is like steering a canoe by paddling only when the current already carries you in the right direction. Unlike silicon chips that require structured inputs in dry environments, nanochemical mechanical computers compute directly inside the medium they monitor. They are not external observers, but participants in the environment, consuming its gradients as both power and signal. This makes them uniquely suited for biological tissues, chemical reactors, or natural water systems where electronics corrode or fail. They act as local preprocessors, filtering and encoding data before any electronic readout. Such context-nabdic computing blurs the line between sensor and processor. Motors in a river sample map pollutant plumes by their trajectories, transmitting results as patterns of motor density without electronic circuitry. It is like tasting soup directly instead of sending it to a lab for analysis. The act of being in the soup is the computation. Computing at this scale will not resemble CPUs or GPUs, but distributed swarms of nanomotors, each contributing bits to a collective inference. Architecture arises from interactions. Collisions, chemotaxis, and feedback loops serve as logic gates and communication channels. Microfluidic chips provide controllable landscapes turning chemical flows into programmable instructions. Libraries of motors with different fuels, caps, and enzymatic coatings create a toolbox of computing primitives. The architecture is fluid, statistical, and embodied rather than digital, discrete, and abstract. A microchip with branching channels encodes a decision tree that motors solve probabilistically by choosing paths under gradient bias. It is like an ant colony solving optimization problems by distributed foraging, rather than a single brain calculating routes. Skeptics will argue that passive probes or clever statistics could achieve the same without nanomotors. Rigorous controls with inert beads, inverted gradients, and deactivated catalysts must show that activity adds genuine information per joule. Measuring both fuel consumption and trajectory field mutual information provides quantitative validation. The greatest challenge is separating motor-based information flow from background noise or hidden biases. If active systems consistently outperform passive baselines under identical energy budgets, the case is made. If not, the paradigm may collapse. Science demands falsifiability, even in visionary computing. Comparing active versus passive tracers in the same microfluidic gradient reveals a 10-fold information per joule advantage for the active set. It is like testing whether a compass points north more reliably than a tossed coin. Proof must be empirical. The paradox is that these computers are weakest in what we usually prize, speed, universality, and raw power, yet strongest in what we rarely measure, efficiency, embodiment, and context. They turn chemical fuel into both motion and meaning, obeying thermodynamic laws while performing computation without wires or transistors. Motion doubles as code, dissipation doubles as memory, feedback doubles as logic. Instead of replacing silicon or quantum chips, they add a new axis of computation, embedded, self-pagered, and near the physical limits of efficiency. Their greatest contribution may be to remind us that information is not only abstract, but also embodied in matter. At the nanoscale, computing becomes behaving, and behavior itself becomes knowledge. A droplet chip where nanomotors map toxin gradients at the energy cost of a few molecules per bit showcases the paradox realized. It is like discovering that footsteps, small and noisy, are the most faithful computers when maps and machines cannot enter the terrain.